So let's go over the homework, crystal and unit cell problems, and we're dealing with the simple close cubic packing structures of the crystals of metals. Okay, and so what we're asking to do here, or we're being asked to calculate, is we're being asked to calculate, okay, the density. So the first thing I figure out, okay, density, I'm good with this. Density is equal to mass over volume. Okay, and what am I given here? I'm given the lattice constant. Now, the lattice constant is the actual, okay, dimension of the length, of the height, of the width. Since it's a cube, it's the same value. And they're giving to me is 0.393 nanometers. Okay, so to find the density, mass over volume. So let's start with mass. So when we do density, it doesn't matter the size of the sample, but since we're dealing with the unit cell, we're going to find the mass of the unit cell. Now, to find the mass of the unit cell, we have to figure out how many atoms are occurring, or how many atoms can fit in this. So since it's a face-centered cubic cell, sometimes called FCC, we can see that there is going to be 6 of these halves on each of the sides. We only see 3 in the picture, but there's a cube and it's 6-sided. So there's 6 halves. So 6 times half. Okay, you can see that's going to be 3 atoms. And then we have these corners, and there's 4 of them, and each one of these is an 1/8, so there's 4 on one side, so 8 overall, and there's 8 eighths, and we can see that when you 8 eighths, and I'm not doing that eighths, so 8 times 1/8 gives me 1, so you could see that this gives me a total of 4 atoms. Okay, that is absolutely vital to doing this, to notice that if we're going to do the density per this volume of this very small unit of repeating crystal, we're going to use the mass of 4 atoms. So what do? Well, we can't look up any number that gives us the mass of 1 atom, but I do know in the reference table there's a mass per 1 mole. Now we call that the gram atomic mass. So we should know for our mole concept, if I go to the reference table, okay, I can see that the platinum has an atomic mass, the top number, of 195.08. Now, if you round to 195, that'll work just as fine. I'm just going to keep it a little more precise. And this is going to be grams per 1 mole. So what I just did here, because I can't find the mass of 1 atom of platinum, I went to the periodic table, and I'm looking for the atomic mass of platinum, which is the mass number usually written on top, okay? And it definitely has a decimal because of the isotopes that exist when it was averaged together. So now I have this number here, which again, right from the periodic table. But the problem is it's per 1 mole of them. So what I do here is I'm going to multiply it and get rid of 1 mole, and I know equivalent of 1 mole, it tells me how many. 1 mole is equal to 6.02 times 10 to the 23 atoms. So I know that a mole of platinum is 195.8 grams. Well, if a mole is actually equal to this number of atoms, well, if I divide by this, notice the moles cancel, I'm going to get the gram per 1 atom, okay? So when I do that, well, before I do that, okay, this will give me per atom, but what did we find? We found that we need the mass per 4 atoms because I'm going to find the density of this cube, essentially what I'm doing. So I'm going to times this by the 4, and that's where that 4 comes from, this 4 atoms, and I needed to know what the crystalline structure and figure out how many atoms. And a face-centered is always going to be the 4. So then I put this in my later of calc, and I get this times this divided by 6.02 times 10 to the 23 times 4, I get 1.296 times 10 to the negative 21. What's my unit? And that's going to be grams per atom. I'm sorry, for 4 atoms. And that's my mass here. So I'm going to use that later. Okay. Now, I need volume. Now, you notice my volume given to me. These are the units I want the answer, and my grams are going to be fine. I'm in that unit. I want centimeter cubed. All right. Well, what do I have? Well, I have the length. Remember, the lattice constant is actually the dimension of one side of a cube. So to get the volume of a cube, or this simple closed cubic packing structure, I'm going to basically cube this, length times width times height. But the problem is I have nanometers. This is not in nanometers cubed. So my first step, party people, is I'm going to take my 0.393 nanometers, and I'm going to convert that to centimeters. Now, some people can do this in one step. I'll often get it wrong, so I'm not afraid to show you. I'm going to do it in two steps. But nanometers, I want to get rid of nanometers, and I want a meter first, because I know how a centimeter is affected by a meter. But again, if you think I'm being foolish in doing this, hey, I feel bad, now I'm over it. But what's the equivalent of a meter to a nanometer? A nanometer is a billionth, 1/1000th of a meter. So if I have 1 meter, it should make sense I have a billion nanometers. Okay, I've set this up correctly. All right, so people have a problem with that because sometimes, again, you could alternatively write what? There's 1 times 10 to the 9, what? You can write this value is equal to 1 nanometer. 1 nanometer is equal to a billionth of a meter. So whether I put this value this way or that way, it's inconsequential. So you could have written it this way. Some people are more comfortable that way. It'll give you the same answer. So I like staying with numbers when I can to make bigger than 1. But if something is smaller than 1, you need a lot more of them to make up for that. So in any case, party people, nanometers go bye-bye. And what do I have? Is now I have meters. And the second thing I'm going to do is convert to centimeters. Some people think that's juvenile of me. But hey, I'm tall. All right, so 100 centimeters is in a meter. And now I'm going to convert my nanometers, okay, into centimeters. And when I do this, I get 3.93 times 10 to the negative 8. And of course, keep your unit. It's a centimeter. So now I'm in centimeters, and I want centimeters cubed, right? A volume is a length times width times height. So all I'm going to do with this dimension, which because it's a perfect cube, I'm going to take the length times width times height. I'm just going to cube this, and that's going to be my volume. So I put that in my calculator. If you have your TI-84, what works nice is hitting the math key and hitting, when you turn your calculator on, okay, you hit your math key and then you type in the appropriate number for the cubing, all right? So in any case, when I cube this, all right, I get it equal to be 6.0698 times 10 to the negative 23, and notice my units are cubed too, and that's the unit I want. So now I'm ready to rock and roll. I've got my, what? I've got my, so now that I have my volume, okay, and we'll do here, now that I have my volume, and now that I have my mass per 4 atoms, and the volume that fits in that side, I can now calculate. So density is equal to the 1.296 times 10 to the negative 21 grams. Don't forget your units. It helps to make sure you're doing these things right. Over 6.0698 times 10 to the negative 23, and that's centimeters cubed. So I'm going to get grams per centimeter is what we want here. So I put that into my calculator, and again, one nice way to do that is use the second function EE. If you're into the caret key, make sure you use parentheses, but put this in my calculator, and I get 21.4 grams per centimeter cubed. Density, platinum is very dense, okay, and that's my answer. So basically, I was finding the density of this little cube, knowing that there was 4 atoms, finding the mass of 4 atoms, that's what this was, and then using the lattice constant, which is probably was gotten from calculations off of X-ray crystallography, when they shoot X-rays and they get diffracting patterns, from that lattice constant in nanometers, converting to centimeters, cubing it, which would be giving me the length times width, that gave me the volume. Okay, so pretty straightforward one, and this is exactly how you did it in the previous homework off the tutorial. Now the other ones get a little challenging, so let's get started. All right, so number 2 is a little more challenging, a lot more actually, but we can do this. Calculate the atomic radius. They want the actual radius, right? So this is the center. Okay, the radius would be what? Half of that. Okay, so this is a radius. So they want the radius in picometers. Notice the question's asking for a certain unit. Now, picometer, 1 picometer, very small, is equal to 1 times 10 to the negative 12 meters. So a picometer is a trillionth of a meter. This is tiny, of the gold. So we know that gold has a face center cubic structure, and that's its density. So they're looking for the atomic radius. Now, the atomic radius can be found by looking at the distance between this point here and this point here, or this point here and this point here, or this point here. So you notice I'm working with the hypotenuse of a triangle here. So all I need to know is the length of my lattice constant, which is the dimension of the cube, and I could calculate what this hypotenuse is, right? It's a triangle, right? I can find my hypotenuse here, and these are my roots, right? These both sides. So the root is going to be, if you're into the math words, certainly that's your lattice constant. Now, once I find the hypotenuse, how many radii do I have? 1, that's half, 2, 3, 4. So this is going to be 4r. So once I find my hypotenuse from using the lattice constant, which is the dimension of the cube, I can divide by 4 to find the radius of the gold. So that's my plan. So how do I execute the plan? Well, how can I get to this dimension? Well, in the other problems, you use the length times width times height of the lattice constant to get volume. So we can get this lattice constant using volume. Now, what do we know? Well, they're giving me the density volume. So density is equal to mass over the volume. Now, I know that this volume right here is the key to the problem, because once I have it, or at least have its value, I can solve for the length times width, right? Remember, to make this volume, okay, it's going to be a length times width times height. And these, what? Individual measurements of the side of the cube are the same because it is a cube. It's the lattice constant. So if the volume is the length times width times height of the lattice constant, which is just what? The lattice constant cubed, to solve for this dimension, we're going to do basically a cube root of our volume. But if you got lost, I'll say it again. So let's clean this up. But we have to get a value for the what? The volume. So what we're going to do, party people, is we're going to use the density and the mass in this face center cube to do that. So we're going to need a density, and we're going to need the mass of this cube to get this dimension in volume. Hope that makes sense. So let's go after the density. And look at this. This is kilograms per meter cubed. Okay? I'm going to put this in centimeters cubed. Okay? Or I could actually put it directly into picometers, but I know the value of meter cubed to centimeter cubed. So I'm going to take my 19,320 kilogram per meter cubed, and I'm going to convert that to a centimeter cubed because I know what the conversion rate is there, or as we talked about in our lab. So we're going to get rid of, let's do kilograms first. For every 1 kilogram, that's a big unit. It's a smaller number. We're going to use what? The gram. There's a smaller unit, bigger number. Kilo means 1,000. So we're going to get rid of our kilograms. Good stuff right here. And now I am going to get rid of the meter cubed. And as we said before, if you've got a meter by meter, okay, by meter of my cube, cubic meter, it's not a bad one. All right, what do I know? Well, that's a pretty big volume, but isn't there 100 centimeters in a meter? So to get the centimeters cubed, you go 100 times 100 times 100, and what you get is 1,000,000. So in 1 meter cubed, you get 10 to the 6th or 1,000,000 centimeters cubed. Yeah, I know that conversion. If I did picometers, I'd be confused. All right, so that's what I'm doing here. Meter, and I'm getting the grams per centimeter cubed is what I want. So when I multiply this through, I get 19.32 grams per centimeter cubed. All right, that's my density. That's important. Keep that to the side because I'm going to plug that in later. We have that. Now I need mass. Well, it's a face center cube just like the other ones. I have 6 halves, right? I have 6 halves, and I have 8 eighths on the corner, as we did with the last one. It's a face center. There's nothing new here. So that's going to give me 4 atoms. So now I need the mass of 4 atoms of gold. So just like we did in the previous problem, to get the mass, I go find gold. What is its mass for an exact mole? So I go find the gram atomic mass in the periodic table, the mass, the atomic, not the atomic number, but the mass number, which represents the grams of gold for a mole. So when I do that, okay, what I get is I get 196, and I'm going to just use more precision here. You don't have to. You could round this off perfectly fine with me. And I got grams, but this is grams per 1 mole. We need the grams per 4 grams. You can see how these problems are very similar. Now, I want to find the mass per 4 grams, but before I do so, I have to find the mass per 1. So 1 mole is equal to 6.02 times 10 to the 23 atoms. And notice what this gives me, party people. Grams, mole goes bye-bye, and I get grams per atoms, or gram per atom in this case. So if I know the mass per 1 mole, if I know exactly the number of mole, I'm going to get mass per gram. Now, I'll kind of jump the gun a little bit. I'm going to times this by 4 because this will give me per atom. So when I do that, do the multiplication in my calculator, let it do the work, what I get is 1.3088 times 10 to the negative 21 grams. And what is this? This is the mass of what? 4 atoms. Now, all I'm going to do now is plug this in up here. Okay, now let's rearrange this. We're solving for V, and again, these are great exercises, these problems in conversions and basics of simplification. I want to solve for V. Algebraically, you should figure out that V is now equal to the mass over the density. That's what we're using. Since we're doing it per this unit cell, mass of the atoms in the unit cell, that's the 4 atoms, over the volume. Why do I want the volume? Because given the volume, I can figure out this constant, this side here, which will tell me what this hypotenuse is. So let's solve for V. I have my mass, which is 1.3088 times 10 to the negative 21 grams all over the volume, okay, which is, I'm sorry, all over the density, okay, which is 19.32. And notice the units, grams divided by centimeters cubed. You should be using your units. Check this out. The grams cancel. And what is 1 over centimeters cubed? Well, what happens is it actually becomes centimeters cubed. 1 over centimeters cubed becomes centimeters cubed. Okay? So that makes a lot of sense. All right, now let's go find that number. And when we do that number, we get 6.774 times 10 to the negative 23 centimeters cubed. Having fun yet? Awesome. So now we have the volume. Now we have a link to this dimension. Remember, the volume is what? The length times width times height, or width, length, and height, whatever dimension you want to call. But because it's a cube, they're all the same. They're all the same by that dimension. So to find the actual dimension that made this volume, all we're going to do is do the what? Cube root of it. And notice the cube root of centimeters cubed is going to be centimeters. And to do that cube root, you do the math function on your calculator, your TI-84, and I believe it's hit 4, and that'll do the cube root of it. And when we do that, you get a magic number. Yes, okay, not really. 4.076 times 10 to the negative 8. And that, my friend, is the dimension. Ooh, that's your lattice constant in centimeters. Ooh, okay. So that's our lattice constant. We can convert to picometers and keep going, but I'm going to do that at the end. It does not matter which one you do. So now I'm going to take this magic number, which is the lattice constant. Okay, now think with me. Well, we said this. We have the length right here. We have this right here for our viewing displeasure. I want to use some basic math to find the hypotenuse. Why? Because I know this is 4r. So what I'm going to do is understand, because it's a triangle, all right, and if I take this sine, I know my basic trig, sine of theta, is equal to the what? Opposite of that angle, which is right here. So it's what? It's going to be the opposite over the hypotenuse. Now, if you have this dimension, you also have this dimension. You could do a squared plus b squared equals c squared and solve for c. That's another Pythagorean theorem because it's the roots of a hypotenuse. But I'm just going to go this way. Now the sine of theta, okay, that's 45 degrees right there. So we'd have sine of 45. We're trying to find the hypotenuse, right? The opposite is our dimension we have, which is what? 4.076, magic number. Okay, centimeter. Okay, and let's go solve for x, or the hypotenuse. You do your simple rearranging, and what am I going to get here? Sine of 45 is 0.8509. So don't forget that this x that we're solving for is really 4r. So let's put that there. That's really what it is. It's 4 times the radius. So let's find 4r. So you do your algebra, and what are you going to get? You're going to get 4r is equal to, I'm just doing this, 4.076 times 10 to the negative 8. Of course, you know what that is, the magic number. And we're going to divide by, okay, the sine of 45, which happens to be, okay, 0.8509. Okay, and we do this math, and what do we get? Is we get, so we get a number, and we're going to divide it by 4. Why? Because I want to find the individual r. There's 4 r's in this hypotenuse, right? So I take whatever that number is and I divide by 4, and that's going to solve for what r is. And I get my radius equal to 1.1196 times 10 to the negative 8 centimeters. Okay? So all I got left is to convert it into picometers. Okay? So to do that, real simply, take my number, 1.1196 times 10, negative 8 centimeters. Get rid of centimeters. Okay, 1 centimeter is equal to how many picometers? Now, understand this. Picometer is small. If you had a number line, this is 1 meter. Kilometer would be over here, right? And this would be decimeters and then centimeters. So centimeters, picometers are way down here, right? So by going from centimeters to picometers, you're skipping what? 2 zeros, or 100 times closer than you were if you're a meter. So a picometer to a meter is 10 to the 12, but since I'm going to the centimeters, it's 10 to the 10. Now, if you don't like that, you could do it in 2 steps. I'm running out of space, so I did it in 1. Ha ha. So I take the number, which is not the magic number anymore, and essentially I times it by the 10. And what do I get? Lo and behold, I get a new fantastic number. Okay, let's put it in magenta, make it a little thicker for the fans out there, and I get 119.76 picometers. Okay, and that is the actual radii of my gold iron. That's this, but again, I got it through that hypotenuse. Interesting, maybe, maybe not. Let's go on to the next problem. Oh, I really like this problem. So what do they want? They want the gram atomic mass. They want the mass per 1 mole. We already have that. We know where to look for that. Well, let's see if we can come up with it based on what we know. So what are they giving me? They're giving me the density, the lattice constant, and we're looking for the gram atomic mass. Okay, so what do I know, party people? I know that density is equal to mass over volume. Now, I'm trying to find the gram atomic mass, but so if I'm going to solve for mass, as you guys should be able to do, mass is going to be equal to the density times the volume, just manipulating the equation. So if you think with this, what we're going to do here, using iron, which by the way has a body-centered cell, we're going to try to figure out, all right, the mass of the atoms in this body-centered simple cubic structure. Okay? So we're going to find the mass of what's in here. Now let's think of it. How many atoms are in here? Okay, we have one in the middle. That's easy. And then we have what? And then we have 8 eighths. And of course, that equals 1. So in a body-centered cube, there's only 2 atoms. So let's go find the mass of 2 atoms and then figure out the mass per 1 mole. So we're going to find the mass. Before I get started, I need the density. So the density is in a unit of kilogram meter cubed. Okay, I want to get to essentially grams per centimeter cubed. So let's do that. All right, meters cubed, and these not a good way for me to start. So let me just do that. So real quickly, I take my, for the millionth time, this is easy now, 7874 kilograms over meter cubed. And I'm going to get rid of my 1 meter cubed is equal to what? That's right, 10 to the 6 centimeters cubed. Kilograms, and also that gets rid of that, and I'm going to get rid of my kilogram. 1 kilogram is equal to what? 1,000 grams, yes. All right, so when I do this biz-nas, what I get is 7.874 grams per centimeter cubed. Okay, now let's go work with the volume. All right, so the volume here, okay, so the constant here is in nanometers. So let's convert that nanometer into a centimeter, since we're dealing with centimeters cubed as our volume unit. Again, I don't know meter cube that well compared to nanometers, so centimeters is the reason why I went that route, like in question 2. So I got my lattice constant, 0.287 nanometers. Convert that lattice constant, which is this dimension, and I'm going to get rid of nanometers. So nanometers go in the bottom, and I want 1 meter is equal to 10 to the 9 nanometers. Nanometers is a billionth of a meter. Nanometers go bye-bye. I've got meters. I know I'm juvenile. I'm doing this in 2 steps, but whatever. Okay, 100 centimeters equals 1 meter. And I do this math, and what do I get? I get 2.87 times 10 to the negative 8 centimeters, and that's my lattice constant. Now watch what I'm going to do here. Using this lattice constant, I'm going to solve for the volume. Volume is length times width times height, and of course it's the same dimension. We've been doing this. So what I'm going to do, party people, is I'm going to cube this. That'll be the same as length times width times height. And it's going to give me centimeters cubed, which will cancel out. That's why I went that route. So 2.87 cubed gives me a 2.364 times 10 to the negative 23 centimeters cubed volume. I've just got my volume, I have my density, and I can, in units that will cancel, let's plug in. So density, now understand this though, we're going to solve for the mass in the cube, so let's get there. So let's go with my density, which is 7.874 grams per centimeters cubed times 2.364 times 10 to the negative 23 centimeters cubed. And I know I'm rewriting this stuff, but guess what? Guess what? Centimeter cubes cancel. That's why I went to that unit. All right? And when I do that, party people, what I'm getting is I'm solving for the mass of what? 2 atoms. So what is that value? Okay? So what I get is I get 1.86 times 10 to the negative 22. And of course, what unit is left standing? Grams. But again, that is for the mass in the cube. This is the volume of the cube. There's 2 atoms. So what I'm going to do is divide this by 2 because I'm trying to get the gram atomic mass, the mass in the periodic table. That's per what? 1 mole. I have 2 atoms here. Let's go find 1 atom. Any way we can go from 1 atom to a mole? Maybe. So let's divide by 2. And that's going to give me a new magic number. You're waiting for it, and you have been satisfied, hopefully. 9.31 times 10 to the negative 23, and that's grams. And that's the mass of 1. Remember, we just found the mass of 2 atoms in the body centered. Now we have the mass per 1 atom. So how do I find, okay, the mass per 1 mole? That's what the gram atomic mass is. It's the mass per 1 mole, as we've been using in other problems. So I know, let's rewrite. So 9.31 times 10 to the negative 23 grams per atom. That's what it is. And guess what? I'm timing it by the all-time leading magic number, and that's Avogadro's number. So 1, okay, mole, I should put here, 1 mole, is equal to 6.02 times 10 to the 23 atoms, or atom, okay? And atoms go bye-bye, and now I have it. Remember, this is the mass per what? 1 atom. If I want per mole, I times it by a mole. So I multiply these babies together, and you get something close to 56.0 grams. And my friends in chemistry, if you go to the periodic table and look up iron, you'll see something that rounds off to 56 grams, and that's the atomic mass, or the mass per 1 mole. Pretty amazing stuff. Number 4, I'm not going to go over. It's choice 2. That's really a simple question. I like to say, really? So I hope that helped. You have a written key if you want something pretty, but hopefully you followed most of this. Most of this, guys, is essentially looking at conversions, having a game plan, and doing some simple algebraic simplification. See you later.